So, the reconstruction process, I have a impulse train which becomes xs of t multiplied by the reconstruction filter hr of j omega xr of t. Now, I want to also at this stage itself look at some of the practical elements of the reconstruction process. So, let's take a quick look at some of the aspects. Okay, so, the ideal reconstruction filter that we have, we already noted the following properties. It is infinite impulse response, it is a sinc function that goes to infinity on both sides. So, I call it as infinite impulse response, and it is non-causal, that it has an impulse response which is non-zero for t less than 0. So, this is not practical, I cannot use this in any practical reconstruction process. So, I need to first of all change this from here. So, for practical applications, the one on the left will not do, I cannot use it, I have to do something different. So, the first thing that I do is not deal with finite impulse responses, we have to truncate it once the amplitudes go below a certain value. So, the first thing that we will say is that we will truncate. Okay, truncate at what point, that needs to be decided, but at least we will truncate to make it something that is manageable. Then we of course it will still be non-causal because you are truncated symmetrically, assuming that you do not to destroy the symmetry properties. So, then you have to shift. So, the shift is, this is to make it finite length, truncate to make it finite length, and the shifting is to make it causal. Okay. So, those are the two things. Now, the another observation or property that we just want to observe is that if I have HR of t, okay, and HR of t minus tau naught, some shifted version, then they have these, both of these have the same magnitude response. Okay, both have the same magnitude response, because the spectrum of this is just a e power j phase term, when I take the magnitude that goes away. So, both have the same magnitude response, okay. Now, take it one step further, if I truncate and shift and truncate, again I do not change the response of the truncated filter. So, the shifting is something that I would say is not going to be an issue, I can always, and phase term which we need to take care of. So, what I need to worry about is what is the effect of truncation. So, truncation essentially means that we have an underlying filter that is infinite impulse response. I will just draw it very quickly, it may not be very symmetric and other things, but I want to truncate it. There are several ways in which we can truncate. We can truncate using a rectangular window, symmetric rectangular window, or one of many windows which have got a smooth transition, smoother than. So, basically you can have a window that has a smooth transition. Okay. So, ultimately the goal is to limit the of the reconstruction filter. So, the corresponding frequency domain interpretation of what we have done, the ideal impulse response is a ideal reconstruction filter is a brick wall filter which goes from minus omega s by 2 to omega s by 2. Now, the effect of truncation means that I am multiplying in the time domain. So, which means I have to do a convolution in the frequency domain. So, convolution in the frequency domain, these windows if you look at their response, basically they are low pass in nature. What you will find is that you will have some low pass response for the window. Okay. Now, convolve these two, what you find is that you have a widening of the brick wall. So, basically the low pass property is retained, zero crossings are retained, the Nyquist property is retained because the windowing does not affect where the zero crossings occur, the spectrum becomes a little bit wider. So, what we can achieve in practice is a reconstruction filter which has got the Nyquist properties that is the corresponding 0 crossings, but has got a response that looks little smoothed out on the sides. Okay. Now, notice that the cutoff point, this is omega s by 2 plus epsilon, it is slightly larger. Okay. Now, this is the main reason why right from the beginning we were saying do not do exact Nyquist rate, need to over satisfy the Nyquist criterion, because any time I need to do a reconstruction filter, the windowing based filter is probably the easiest way to do that, need to over satisfy the Nyquist criterion. Why? Because I do not want aliasing, and basically I want to make sure that I can apply a proper filter without distorting the signal spectrum. So, do not do the Nyquist sampling, basically which Nyquist sampling means that do not do this type of sampling, this is not what we want, but instead go for something where the Nyquist sampling is over satisfied, and that will help us achieve with the practical filters, we can do the reconstruction. That is why we say that always we want to over satisfy the Nyquist criterion. Okay. So, basically choose your sampling frequency to be greater than 2 times omega naught, the band limited signal. Okay. So, again I hope what are some of the we need to keep in, and of course the key elements there. I am sorry. Okay. Okay. So, the very good question. The question is why am I trying to truncate and not try to actually use an ideal filter. See, again we are going back and forth between what can be realizable and what can be not realizable. So, this green line, basically a brick wall filter, even in the analog domain I cannot realize it. So, the way to visualize it is why am I not able to realize it, because that is a brick wall filter. And one way to think about it is because this is a filter that will be infinite in terms of, and it is non causal. So, how do I get, so basically you move over from the continuous time to thinking about saying, okay, if this is the property that this is why it is not realizable, basically the brick wall, even if I say use whatever order Butterworth or Chebyshev filter, you will not get a response like this. So, what is it that we can achieve? What you can achieve is something where the edges are not like a brick wall, but some sort of tapering is occurring, and that basically says, you know, to sort of link it to what we are familiar with. If you had an impulse response which I then window, then shifted, then I would get first of all a causal filter which is realizable. The second one is it will be it basically what I am saying is the windowing plus the shifting gives me a realizable filter that can be again equated to either a Chebyshev filter or a Butterworth filter in the analog domain, and say that okay, whatever is the best that you can do, and you will find that most of the times the best that we can do in terms of the analog filters will be of this form, right. So, it is the brick wall is not, and how do we make it to go from there to something that is realizable. But a very important question, because very often we are trying to make that link, and again in fact during the course of this lecture itself we will come to one more such non-realizable condition which we will have to change, because in the reconstruction process, if you notice, I assumed a block which is not realizable. How do I generate Dirac deltas? I can't do that. So, what is the next best that I can do instead of a Dirac delta? So, this is again maybe it is a good that you raise a question. So, basically what we are saying is this is what we need to generate, right, corresponding to the impulses x of n, Dirac deltas which are spaced by Ts. These are Dirac deltas. Now, this again very difficult for me to generate, but what we can generate in practice is something which is of the following form. So, what we call as a sample and hold. So, you take a certain value and then say okay, it is a rectangle approximation. So, sample you holds it until the next sample comes along. So, the next sample comes along. So, instead of a direct deltas of the proper scaling, I get a sample and hold circuit. Now, what is the impact of a sample and hold? So, that means my reconstruction filter now has to change, because now I have changed the continuous time signal. So, what is the change in the reconstruction signal in order to make it realizable? So, that we will answer that question, but good that you asked, because always important to know how do we go from something that is ideal to something that is realizable. Very, very important. That's part of our the thing that we want to help and okay. So, again feel yes.
Like this truncating and shifting business, we even have to do it with the digital anti-aliasing filter as well?
No, digital anti-aliasing filter, you can specify it as a causal filter. So, you of course, you can design digital filters that are non-causal and then do the shifting, but there are several filters which again when we come to it, maybe we can make a statement, but let me just sort of make a statement, and this is in the last page of the. So, in the context of digital filters that you asked, so a digital filter. Okay. So, now we said that we have a digital filter which has a certain response, and we can specify, and the cutoff happened to be pi by 4, minus pi by 4. Now, there are several methods that Parkes-McClellan method, which designs for us a equiripple optimal filter. Okay. Parkes-McClellan filter is also a linear phase filter. Now, again I would like to refresh or recall to your mind, there is a relationship between linear phase and zero phase. Zero phase requires symmetry in the time domain, right. The Parkes-McClellan filters are centered around 0 and that are non-causal, that is the zero phase version. But because they are finite in length, you can always shift them to get a linear phase filter. The minute you shift a zero phase filter, it will become a linear phase filter. So, what you will get is a so yes, you are right. If you want zero phase, it will be non-causal. But if you are willing to take a linear phase filter, which is perfectly okay, because in our case the reconstruction process primarily has to remove the spectral copies. So, which means that linear phase filter would do the job equally well. So, a FIR filter designed by one of the methods like the Parkes-McClellan method would satisfy the requirements for what we are looking at in terms of reconstruction. But yes, is there a zero phase version of the same filter? Yes, there is, because if you look at it as a filter with time domain symmetry around omega n equal to 0, then it will be zero phase and symmetric. You shift it, it becomes linear phase with and causal. Okay, good, very good question.
Because of truncation, now motor reconstruction window filter have side lobes coming into picture.
Yes.
So that won't that give an aliasing effect?
Okay, very good, very good question. So, the question is when I do the truncation, right. Let me see where do I have the truncation figure. Okay, here it is. So, the question is how do I design the truncation such that I do not run into aliasing effects. So, this is precisely where the over satisfying the Nyquist criteria will come into play. See, even if it has a ringing effect, let me see if I can highlight this. Okay. So, here is a ringing effect, but you notice that based on what filters we design, we can have the ringing to be minimized. So, in fact, there are filters which have got the following type of behavior. So, it goes like this and then pretty much stays down. Okay. So, there are certain windows that have got very low side lobes. Now, you would use something like this to make sure that you do not have ringing. Again, the reason I used a one with ringing is to show that you should not forget the fact that when I do truncation, there will be some side lobes which you have to worry about. But there are filters which have very low, and so what will happen is this part will get widened, right. Your the main brick wall part will get widened, but you are over satisfying the Nyquist criterion. So, once you over satisfy the Nyquist criterion, you can make sure that the windowing, yes, it will have ringing, but it will die down at some point, and it dies down before the aliasing part begins, right. Very good question. The reconstruction filter is an analog filter, but just like we did anti-aliasing, where we did a combination of analog and digital, we will find that we can do a combination of analog and digital as well, because what you can do is you can do oversampling of the digital signal, so that your spectral copies now move further apart, correct. When I do oversampling of my digital signal, it will move the spectral copies further apart, and then my analog filter just has to get rid of this thing. So, yes, the last stage of the reconstruction has to be an analog filter, but it does not have to be a high Q analog filter if you have incorporated some of the multirate techniques.
You can't downsample it in, like, I mean to ask, why are we truncating it in, why are we bothered to truncate the impulse response of an analog filter? Because
no. Wait. Please ask your question again.
The filter we are trying to work on is an analog filter, right?
Correct.
We are trying to truncate the filter to make it limited, the impulse response.
Well, if you want to visualize it from an impulse response point of view, but you may not implement it as a convolution at all.
Yeah,
the last stage may be just an analog filter. So, I am using this as a way by which to explain how do I go from a non-realizable filter to a realizable filter. Where do I have to pay the price? The price will come in the fact that I cannot get a brick wall filter, but I will get a filter with a finite transition, right. That is all. As long as we are comfortable with that, this red line will be an analog filter, right. But in terms of the visualization, we can think of it as, okay, the way we achieved it was by changing the underlying property of the ideal reconstruction filter to match something that is so, because the windowing sort of gives us a way explanation as to why the spectrum became rounded. You did not have a brick wall response. Why did it become greater than omega s by 2? Again, that is because of the windowing and the ringing that will come in because of the windowing. So, any practical filter will be of this type, which means that yes, I need to be oversampled with respect to Nyquist rate. Very good. Okay, I am not sure what is the time. Okay, so let me just sort of give you something for you to think about as you prepare for the next class, and we'll just spend a minute to highlight what it is that we need. So, basically I would like you to review Oppenheim and Schaefer chapter 2, all the elements of discrete time signals, of discrete time systems, the LTI properties, how does it manifest itself, and also the notions of causality, and when do we say something is non-causal, when do we say something is anti-causal. Again, these are just basic definitions, but I would like you to be comfortable with that, and I would like to look at several some simple examples. And again, one very unique property of the discrete time signals is the discrete time sinusoids. Okay. Again, when will there be periodicity? Not all discrete time sinusoids are periodic. So, look at what is the conditions for periodicity, and maybe as a simple test case, what I would like you to do is look at the following example. Okay, I will just write down the question and then request you to try it out so that we can then look at it subsequently. Okay, so if I have a sequence x of n, which is 1, 2, 3, 4, 5 with an arrow under the 3, that means that is the origin. I would like you to obtain the following sequences that are obtained from this. 1 y1 of n is x of n minus 3, basically that is a shifting of the sequence. Second, y2 of n is x of minus n, time reversal. y3 of n is x of minus n plus 1, that is shift and time reversal. Fourth, y4 of n is equal to x of minus n minus 2, again shift and time reversal, little bit you have to be careful when you do the shifting. And the last one is y5 of n, x of 3n minus 1. Okay. Now, I am sure you are familiar with this, I am sure you would have done lots of examples. What we would very much like to focus on is the last case, because that is taking us into the multi-rate domain, because what we are fundamentally doing here is changing the sampling rate. In Oppenheim and Schaefer it is called time scaling. Okay. So, please look at time scaling, very important. You can either increase the time scale or reduce the time scale, and the most general form of time scaling is y1 of n equal to x of m by n into n. Okay. Now, the exact definitions of the time scaling are all present or given in the book. This is the form that we are most interested in. Okay. So, please make sure that we look at it. I think I have lost power, but let me stop here. Basically look at time scaling, basic operations with a focus on time scaling, because that is what I would like to pick up in the next class. Thank you.